Good evening, everyone. Welcome to this talk, Machine Learning for Developers, How to Build Even More Intelligent Apps and Services. My name is Dan Greco. I am a senior software engineer at the Algorithm Data Science team in Cambridge, Massachusetts, right across the Charles River from downtown Boston. We work with, our team is primarily based to work with Tier 1 customers, ISVs, and partners to come up with solutions, machine learning solutions for problems that will help them in their business. The team is primarily made up of data scientists, and there's a handful of engineers like myself who work with them. And I've been there for 3 years and didn't know a lot about machine learning or data science when I came in. I can't say I know a ton of it right now, but I have learned quite a bit working with these guys and girls to learn some of their terminology, how things work, and it was really helpful for me. And in doing so, I thought it would be helpful to talk to other people about it too. So today, during this talk, I want to cover some of the topics about machine learning, some of the things that data scientists use when they talk, show you some of the paths you can take when you implement machine learning into pipelines, and then a demo that puts it quite a bit of it back together. So the talk is about machine learning, and the question a lot of people have is, what is machine learning? And many people have many different variations of it. They think it's artificial intelligence, they can think of it as robotics, or any number of things. But what's important here is, what does Microsoft think about machine learning? And that's why I'm here to talk to you, is computers that become smarter with experience. And it's just like you and I became smarter with experience, and you can think about models like that. But experience in this case is past data and human input. So we talk about data, how the data scientist talks about data, and that's training data. So training data, you can think of it as a table, a CSV file, a SQL table. It's rows and columns. And each row is a sample. And a sample is a single observation in that data set. A sample is made up of features, and features are individual columns within that data set that is going to be needed by the model to give you some type of prediction or some type of answer. And potentially, we have labels. Label is a historic result from a given sample. It's the ground truth of what happened. And it's not necessary to be with your data, which gives you two different types of learning. There's supervised learning and unsupervised learning. Supervised is when you have the labels in there, and you're inferring a function from your labeled training data. Unsupervised learning, you're finding patterns and relationships within that data. And I'll cover a little bit more about that as we move forward. Now, the human input, this is really the domain of the data scientist and a subject matter expert, two people that are absolutely critical to solving a problem. And in this case, sometimes it helps if you put it somewhat into context. So if we had a question, how do we determine blood alcohol content from the number of margaritas somebody drank, we're going to need to know your body mass, number of margaritas, and label it with the blood alcohol content. So we get to the first point here, relevant data. Relevant is body mass, number of margaritas drank. What's not relevant is the Red Sox batting average, or did they have a drink on a Tuesday, or was it Sunday afternoon? Those become irrelevant data, and the experts, the data scientists and the subject matter expert, help weed out that information. What is not needed to solve this problem? Then it's connected is the next step. Connected just simply means in our rows of samples that the values actually exist in those columns. If we only know body mass and the label blood alcohol content, but no margaritas, we can't really set up a good model based off of that. We're not going to be able to do so. If you have a sufficiently large enough data set, you can still come up with a model and it will be accurate, but you can't have too much disconnected data. So the data has to be relevant and it has to exist. And I think that kind of makes sense. The next one is accurate. Accurate is exactly what it sounds like. The data is what you say it is. The body mass was correct. The number of margaritas was correct. The blood alcohol reading was correct. Because again, without correct fields in there, you're going to come up with a really bad model. You'll come up with a model, it just won't work for you. And the last one is enough of it. So let's say we have some great samples and we're sitting at a local pub and we're recording this, and in comes a guy. He has 5 of them where this guy should be on his lips based on his reading, but it's a 0. So our data was invalid, right? We missed something in the data, and that is the volume of alcohol in the margarita, because we didn't anticipate someone drinking virgin margaritas. So we have to have enough samples in that data, reiterate back on it, okay, we missed a feature that was really important, so let's put that back in and let's get more and more samples of the data. The last thing, and really is the first thing, but when you talk about it, the last thing is a sharp question. And a sharp question on your data has to be able to be answered with a name or a number. Vague questions don't work when you're creating a model, right? If it doesn't ask for a name or a number. So if I take all of this business intelligence and bring it up to the cloud, and then I ask, what can I do? There's no one in this room who can answer that question, because we don't know what you mean by what can I do. But if I ask a question, which vehicle in my fleet is going to fail in the next 30 days, I can answer that with a name and a number. So sharp question is absolutely imperative when you're getting your data to get ready to create machine learning. So the types of machine learning problems you can solve. My team specifically works on a lot of predictive solutions for different companies, and a lot of it has been publicized. So we've done a project with an international jet manufacturer. Jets, if anyone knows anything about jet engines, parts have a soft life. They come out at the soft life instead of the hard life for obvious safety reasons. But if a part starts to fail or starts to exhibit behaviors that it's going to fail before its soft life, we built a model for them that will tell them that on the specific engine, these parts look like they're not going to make it to their soft life and they have X number of days left. It helps them with their return, because when the plane lands in Stuttgart, they already have an idea if a part needs to be replaced. We have a part, we have a mechanic, we have time on the runway, get the part fixed now. As opposed to waiting in the past like they did, where the plane gets out to Singapore, say, and they find out the part's no good, but they don't have any in their storeroom. Now the plane sits on the runway, flights get delayed, cancellations, nobody's happy as a traveler. There's another one with an elevator company. It's very expensive to send a mechanic out to a site to fix elevators, and we work with a company that has millions of installations globally. We help them predict when parts are going to fail and what types of parts are going to fail on their elevators. So if a mechanic is sent out to 1 Main Street, and we know, based off of the model, that there's another elevator on 5 Main Street that has a shaft door issue, the mechanic can just be sent over there, and it's a huge savings for the company over the year. So those are types of prediction problems, and that's a supervised learning. Another supervised learning is a classification problem. And I'm going to mention this because it's part of a demo later, is sentiment analysis in text. So you feed it in text, and it will tell you whether the comment is positive, negative, or neutral. So it can classify information. Or unsupervised learning, we have anomaly detection. And that's really just saying, is something really weird here? Is this reading out of the ordinary? So if we look at the difference between prediction and anomaly, take 2 factories that your company owns. One of them's been around for a decade, lots of readings, lots of labeling of data. We know pretty well how that is operating. We can set up a predictive model. Before a production run is set, you can set the mechanics out on the floor, fix that line. But in the case where you have a brand new factory and it's never failed, all you have is sensor readings that tell you how it looks like when it's running fine. You can set up an anomaly detection that says, hey, there's something really weird going on here. Now, it's not going to be as accurate as the predictive model, but it is going to give you an indication that something needs to be fixed. Now, over time, as you collect more and more data, you can go back and retrain that model and put it into a predictive model and, again, get much more accurate results. And clustering is another one where, so you've listened to this type of music, you're probably going to like these. You've watched this movie, you'll like this TV show. That's kind of clustering. And it's worth noting here, even though it's not on the slide, what's become really, really popular in machine learning world, even though it's a little bit deeper, is called deep learning. And a lot of people have seen that. It's image detection. We have some of those things with howold.net that could tell you how old you are. But these are much bigger models, and I just wanted to mention it. So once you have decided that you're going to use machine learning, you have your sharp question to apply to your data. Your data scientist and your subject matter expert have gone over that data, filtered it down, come up with what they believe to be a good training set, and now you have to figure out how you're going to implement it. So your first option, or option A, is going to be a pre-built solution, something that you can take right off the shelf and use. So the Azure Cognitive Services API has 5 categories, and there's a little bit of a typo here. That's 20-plus APIs that are already built. So we have speech APIs, which are text, or speech-to-text, language, so text analytics, sentiment analysis, keyword location, language detection, vision that picks up the emotion, and that howold.net, you can use it for that kind of things. Knowledge, so recommendation engines, and search, such as Bing Search. In your Azure subscription, you bring that API in, you get your own key, you don't have to do anything else. You can now have a RESTful endpoint that you can call from any of your applications. The next option would be Azure Gallery. So in the gallery, and I have a link here, and I believe we're going to share all of this stuff with you after build. You'll get some kind of follow-up. You have pre-built Azure machine learning experiments. There's a lot of them out in the galleries. Most of them come from Microsoft. Other people have put some out there. They may also solve your problem or be pretty close to solving your problem. If it's already solves it, you just bring it into your ML Studio, you build it, you publish it, and you have a RESTful endpoint. If it's close enough, you can do some modifications to the experiment right there in ML Studio, then publish that, and now you have an endpoint. And again, it's consumed through a REST endpoint. So as developers, we're used to putting all the rules in our applications. In this case, we don't have the rules in the application. We can have that logic sitting out behind a REST endpoint, and the application or service or server can get those answers by feeding it in data and getting its results. And if we decide the model can be better, or we go from, say, an anomaly to a predictive type of model, assuming we don't change the inputs and outputs of that endpoint, we have a smarter model in the background without changing any of our downstream applications. The next step would be, we can't find something out of the box, so let's do a manual solution. So the first one here is Microsoft R Server, and we can lump in now SQL 2017 that has R and Python built into it. But Microsoft R Server, you build models in R. R is the language of the data scientists. Most of them are learning that in universities when they come out. This is what they're comfortable with, R and Python. You can build models in R. It's scalable with Spark, Hadoop, HDFS file systems, and similarly can be consumed through a REST endpoint from Microsoft R Server using deploy R on your model. Now, it is just an R model, so you can take that to any system that has the R infrastructure on it and run it there. But again, you probably want to put that out behind an endpoint so that if the model changes, you don't have to change all of your applications. You don't have to go to all the installation sites and fix it. The next one is Azure Machine Learning Studio. And this is kind of a jump-in step for a lot of data scientists into machine learning and for developers who are interested in playing with it. You can see the link here. So it's a visual composition. It's a web-only tool, and the models are web-only as well. This is where you would pull in your Azure Gallery. Lots of first-class or best-of-class algorithms built into it and lots of modules to do data science work. But if you find that it doesn't do something that you need it to do specifically, it is extensible with R and Python, where you can drag out R and Python modules, put in that code there, and then have that be part of your graph. And again, just like the gallery, it's consumed as a REST endpoint. So I have been doing, I did a talk at the AI Immersion Day. I think some of you may have been there. And I've been working down in the expert zone. And I've got a lot of good feedback and running through this little quick, so I'm going to just throw something together really quick. So we have an example how we could use ML Studio. We have a factory. We have a bunch of gadgets that all report the same kind of information on our production line. Rotation speed, temperature, voltage. It's made up data, so it's not real, but we can create a model from it anyways. We have a time and a date. It was a time, not a date, just a time, which is an integer. We don't care about the date timestamp. We just want to be able to tie results back to a device ID. So it's device ID, time, those three fields. And we've had our subject matter expert go through and tag everything the state, 0 being not an error, 1 being an error. So we've created that data set, and we can come in here and create an experiment. Now, you can see here we have a bunch of the experiments already visible, so we can view other stuff in the gallery. But for this example, we don't have anything that's already there, so we're going to start with a blank experiment. First thing we need to do is bring out our training data. And just to show you what I was talking about, we can visualize what the data looks like here, and these are the exact same columns that I just explained to you. Notice that the time is just a rolling integer. Again, we just need something to tie the result back. So the first thing we need to do is split the data. Because if you talk to any data scientist, that's one of the most important things when you're training a model, is to split that data out and train on some of it and score on some of it. If you push all of it through your training, you're going to end up overfitting your model, where if your values come in exactly like you had in your training data, it's going to work fabulously. And if you have values that fall outside of those bounds, not so fabulously. Could work, probably isn't going to. So it's better just split your data right off the front. So now we need to train a model. And as I mentioned, we're going to score it. And I'm just going to drag out a couple more boxes here so we can connect it. So to train the model, we want to take data. And if we look on the right-hand side here, we're just going to do a 50-50 split, random 50-50, half to train, half to score with. We're going to take the other half out. Other half out. We're going to score with it, and we're going to score with the model that it trained on and connect the evaluate model. But train model needs a model to train on. So we know that our field is a 0 or 1, our state field. So given that it's a 0 or a 1, we have a two-class problem. So given that we have a two-class problem, we can come in here to search and look for two-class and find that we have quite a few of them. Now, in another talk, I go through a couple of the examples, but because I'm throwing this in now, I'm just going to tell you, based off of experience, out of the box, two-class boosted decision tree for this problem is going to work the best. And we connect this to our train model. But train model, it needs to train on something, and that's the label, because it's for supervised learning. So now we have to tell the train model exactly what we're training on. So we come in here and we pick states. Done. And then we need to run it. Make sure our model is going to work, our experiment is built appropriately, the graph will get checkboxes down it, and because my data set is not huge and the training is not that difficult, we can come in here and have a look at the evaluate model. How did we end up doing? And this graph is really important to a data scientist. It really is they look at the area under the curve. How much of the problem set did they solve at that pass? And in this case, we've got a 94.7%, so almost 95% accuracy. Data scientists aren't going to be happy with that. In most cases, they're going to want it to be high 90s. But for this example, we're not going to muck with it. We'll say, it's great, that's all we need. So given that it works, we can set up a predictive web service. Now, we can set up a training web service, too, which would retrain the model behind the scenes periodically. We can set up services to execute that service. But we're just going to run this as a predictive model. Now, we know in our example data set, which is feeding into our REST service, and this is the infrastructure for the REST endpoint that's going to be created, we know that the example data has state in it. But if the device can tell us state, why are we even doing machine learning? So we know it doesn't give us state, so we need to filter that out from the inputs. So again, we can come over here and do a select columns and data set. I'm going to actually, yeah, we can just connect this from our data set and into our output. We can use the column selector here. We want all of the columns to come in except for state. Done. So we've adjusted the front end of our API. On the back end, on the result, if we don't do anything with the score model, we're going to get all of our input features too. But we don't want that. And generally, when you have a problem, there's a lot of different features. That's why we have the time and ID. We really only want the time and ID to come back out with the score result. So let's take this column and data set, Control-C, Control-V, drag it down here, connect that up, and then we are going to launch the column selector again. We do not want temp volt rotation speed. We want the time and ID. The scored label is going to be the state, the 0 or 1 state, and the probability where it fell in the range so it could make that determination. And we say, OK, we're going to run this as well. And again, you run it to make sure it works. It's going to not bomb out on you if you publish it. And again, the graph's going to go pretty quickly. It's a very small data set. It's not that hard. Although the select columns will take a while, we can just take a quick look at the output sets. It has the 4 columns that we were expecting. That's perfect. So now we're going to deploy it. And when I click deploy, when it's done, I now have a live REST endpoint out on the internet that anyone can call to make use of it. And by anyone, I mean any client that can form an HTTPS request, right? Everybody knows a RESTful endpoint. As long as you can make that request, you're going to be successful in calling it. We have an API key that's good for each of these calls right here. We have request response and batch execute. Request response is a synchronous call. We give it 1 sample. We get 1 response immediately. Batch can be used when you're processing large amounts of data on a daily, every few hours, monthly, whatever that is. You set up a process that will execute batch on a set of samples and give you a set of results. You get a job ID when you launch it, and then you can check on your job that way. But when you look into either one of these pages, it's going to give us information such as my URI for the experiment. I come down, it tells me what my headers need to be, what my input package looks like, what my response header is going to be, my response package, the types of those data on the input and outputs, but at the very bottom we can see C#, Python, and R, and this is all example code to call this very experiment. So if you copy this code here directly into Visual Studio, into a console app, use install package on the NuGet package manager, scroll down here, replace your API key, you can execute that, and it's calling the endpoint we literally just published. So it gives you a great way, while you can roll your own connections, you can use these examples, and it just simplifies it for you. OK, so that's Azure Machine Learning Studio. And for a final one, just to throw it out there for the deep learning crowd, is we have Azure Cognitive Toolkit and TensorFlow. And these are both more complex and more powerful, typically associated with deep learning scenarios because you need to train on massive amounts of data. And typically when you're doing that, you're training on GPUs because you need it to process a lot quicker. It does create portable models. Now those models can be put out behind an endpoint and then wrapped in code. Both of them can be run in the cloud or on a server, assuming the infrastructure is there, and you wrap them with custom code. So Cognitive Toolkit, you can call it through C++, Python, C# or any .NET language. So you can move that around for you. And that's really, I just wanted to make that known that outside of the other tools that I'm talking about are the deep learning. Deep learning is definitely supported on Azure. And then we have a combined solution. So we can seamlessly blend different technologies where we may need to use some custom code or Python or R, and we also can use a package toolkit. And there's a number of ways to do that, and if I went through all of them, we would be here for hours. So I picked out one, Azure Data Lake Analytics. It is USQL based, which gives you the power of SQL-like queries with the expressive nature of your own code. You can write C# directly in your queries. It does, like a WinForm, have a code behind CS page, but you can then bring in your own libraries, register them with Data Lake Analytics. And you can use R and Python, which are extensions that are supported. And it also has cognitive services that is built into Azure Data Lake Analytics. Now, it's not the Cognitive Services API. It is a version of the cognitive services that exist, those number of categories that I told you about. Because if it was an endpoint, we're talking Data Lake Analytics, we can perform huge queries. Can you imagine what a server is going to do when we try and hit that REST endpoint 10 million times when we do a query? We're going to get denial of service, blacklisted, and so you cannot call external APIs during a Data Lake Analytics USQL query. And you can craft them right in Visual Studio. So I want to jump now over to Visual Studio. Let's get rid of that job. And so I've got a test SQL. So here this is a USQL query. So we do a reference assembly for the text sentiment because I'm going to use sentiment analysis. And this is a subset of the bigger demo at the end. That is, it's piling in data coming in from a stream, putting stuff into Azure Data Lake Store in a partition way based off date. Each file is created on a per hour basis. And so I want to just do an example query here on one of those files. Yeah, I noticed someone trying to make it bigger here. So we do the reference assembly. We declare variables at the beginning. And as you can see, we use C# variable types. So I'm going to create a time. I know I have data in the store that's back on April 19th at 10 o'clock UTC time. And we're going to put an end date on it as an hour. We do an input file set where we can add in a virtual column here that will be filled in, and Azure Data Lake Analytics will deal with that for us. And then I have some outputs here. The first one is a map. So these extract statements are essentially a map over your data set that tells the system, this is what's in this column. This is the type of data, and this is what I'm going to give it a name for other queries. We come down, we're going to do a select out of that set, and we can use our virtual column here to say we only want times on that folder structure to be within here and here, and for the hour, so we can limit it to the 1 hour. Otherwise, this would run for a while. Now we're going to call sentiment analysis. And this is the call right here. We set up this query to process the data using the sentiment analysis, and it's going to give us a result out of that, which is going to be these fields here. And then we're going to output the data. And then I'm going to throw another little query in because I'm not actually using any of the other query stuff. But on that same set, I want to group by product ID and count how many of them I got for that in the past hour. Now here, I can run this locally, or I can run it on any of my Data Lake Analytics accounts and submit it. And it will take this query, package it up, and it's going to push it to Azure, to that Data Lake Analytics, submit a job for me. And hopefully, because it's a demo, it'll probably take a while. But it usually doesn't take too long. You can see it has a few stages here. It's preparing, getting the query ready to be submitted, compiling it, make sure it's OK. It's going to queue it in the list. It's going to run it, and then give us a result. And it usually takes about 1.5 minutes. So I'm going to fingers crossed that this is going to work relatively quickly, but we can always come back to it if not. But we can also go to the portal and see job execution. But for development purposes, being able to use Visual Studio to write this, to test out your code, to test out your queries, push it against a local store that you can use for a test, or kind of hang out and wait for these queries to go against the Azure system, it can take a little time. So we can see that the job is queued, and now it should be running. So now we'll start to see some more activity. We can see the first bit of the graph, so that's the extract, so that's the map over the data. Then we have our two processes. One's going to be calling sentiment analysis, one's just going to be performing aggregates on a per product ID, and then dumping them out into different files. And so the aggregates is done, sentiment analysis is going to take just slightly longer. And I'm crossing my fingers, this goes relatively quickly. I'm sorry about that. It works really fast all day long. But you know how it goes. You get on stage and everything slows down. So we can see that the graph has gone all green, so it's executed. It should be giving me a finalized version of it. We're going to take a shot. I can double-click on the result. The result is written out into my data lake store, but it gives me a sample of what I produced. So I can check to say, yeah, that looks about right. I only have one of these IDs. That's great, because we've sorted it by ID, so fantastic. And then we can go back to the job and say, what did our score result look like? What did we get out of the sentiment analysis? And we can see the time the review was put in, the product ID. The next column is the actual comment that they gave, and whether the analyzer gave it a positive, negative, or neutral response. So we were able to do that, run it against SQL right from our laptop, without having to get on the portal and write the queries there, which makes it pretty handy. Okay, so great. So we get to the demo. This demo is, we own, for the story on it, is you have a website that sells a lot of products from a lot of different distributors. Given those products, we're having a lot of complaints about certain products, which is costing us money for returns and reprocessing those claims. So we want to figure out which of our distributors we want to drop from the list. Which ones do we want to stop selling their products? So our sharp question is, which products do we want to get rid of? So what do we have for data? Well, we have a lot of data streaming in online from clients who have bought stuff and come back and give a review on the product. So part of a bigger picture, obviously, is we can try and map returns based off of comments for a product, but one of the things is we need to figure out what the sentiment is coming in from those comments online. So we have our pipeline architecture. Given that we're doing sentiment analysis, and I just showed you cognitive services sentiment analysis, we have something out of the box we can use. So we're going to build a pipeline. So this is an example architecture of a lot of different, we do a lot of these things for customers, the tier one guys, for even examples. So there are, if you've heard of Cortana Intelligence Quick Start or the Kix Gallery, there's a lot of examples out there, example architectures that give you different ways to solve different problems. And this is kind of how the architectures go. So we have a data source, and in this case, this is going to be our user feedback. I just have it set up right now using a web job, just pumping through a couple of sets of comment files, but this would be live coming in. It's feeding into an Azure Event Hub. So Event Hub is a big pipe you can shove out onto the internet and access it through a REST API. There are also Python and C# libraries produced by Microsoft that make this very, very easy, couple lines of code and you're in kind of thing, but you can scale that, right? So all of these services are very scalable. I didn't need to scale it too big for this one because I don't have that much data coming through. But the Event Hub will store data for some number of days. So if your back-end processes, something falls down, you don't lose the data. You can go back and reprocess it at a later time. How we're processing that or preparing the data off of the Event Hub is the Azure Stream Analytics. Now, this is a near real-time analytics on a live stream. I'm not really doing a lot with it in this way, but you can hook up your own Azure ML endpoints right in Stream Analytics. So you can call Azure ML as the data is being streamed in, perform some task, and output it. Stream will take it not only from Event Hub, but from storage blobs it can read off of, and a couple of other things. It can also output to any number of sources. So we can go right out to Power BI datasets. We can go to DocDB, Redis Cache, SQL Data Warehouse, and in this case, we're using Data Lake Store. Now, in a real enterprise environment, we would use something like a store or a SQL Data Warehouse because we expect huge volumes of data to come in. Now, just because it says Data Lake Store, it doesn't mean that, oh my God, it comes with a huge price tag. It doesn't. You're paying based on storage and access of that data. So if you didn't actually need such a huge store, you're not going to get killed with a huge price. You're going to pay for what you use. So the store comes in, the data comes in, we're going to partition it coming out of Stream Analytics. Stream Analytics allows us to do that. And then every now and again, we need to periodically execute some functionality on this, this raw data coming in. And that's where we use Azure Data Factory. So Data Factory can orchestrate, schedule, monitor what's going on. It can pull data from your on-prem SQL. It can pull it from a number of different places. And it can do a lot of different bits of functionality. You can run Hive scripts against an HD Insight cluster. We can run uSQL scripts. We can copy data. We can run just regular SQL scripts against the SQL server to copy data out to move it along in a pipeline, process it. We can call ML endpoints from Azure Machine Learning Studio. And in this case, we are going to call a uSQL script. Now, the script, what it does is first says, OK, I'm going to run the factory every hour because I'm expecting huge numbers of data, and we want to stay on top of it. I think it's probably unrealistic for an actual environment for somebody else, but they would probably run it once a day. But I'm going to run it once an hour. So it's going to go back. It's going to take the last hour's worth of data. It's going to process it, score it. Then there's another activity. So in Data Factory, it is a dependency graph. So you have a data set. The first activity will produce, it gets that data set, produces another one, which will then trigger off the next activity, so you can guarantee your execution flow. The next activity is going to be roll out the aggregates, how many positive, negative, total, neutral comments I got per product ID, and then there's one more activity that's going to roll them all up so that we can then visualize it out on a Power BI dashboard. Now, would that be the end of the step? No, we already talked about we would need to also tie in actual returns, right? People can complain a lot, but they may not be returning the product. So if they're not returning it, maybe it's not really that big of a problem. But this example is not going to address that larger problem of bringing in other data sets, other model results, and then coming out with other answers. We just want to be able to visualize it so we can make some business decisions of what do we really need to investigate. OK, so now we're going to jump over to the Azure portal. Nope, not that one. This one. So when we get out to the portal, you generally organize your services out from a resource group. And then it's a good way to group all of like services for a specific problem in one place. These are all of the services that I need to create this. And we're going to walk through quite a few of them. But this gives us an overview of what's going on. So the first step that's happening is we can go to our Event Hub. Our Event Hub shows us how many comments or how many records are being read, written, and show you the activity. So you know that it's live, everything's working, and it's moving along. Again, it will store data for some number of time. It's configurable to how much it can handle. But the Event Hubs can take a huge sum of data. The next one should be, we're going to have to go back because I lost it. It's going to be the Stream Job. The Stream Job is reading out of the Event Hub. And the Stream Job you set up with a few different things. So you need to set up one or more inputs and one or more outputs for it to actually execute. And then a query in the middle. So our output, like I pointed out before, to Data Lake Store, you come in here and configure this, excuse me, tell it which data lake you're going to, and you can set up your path, and it will do a macro replace with the date format, time format, based on the record time coming in. So we get a nice, clean partition out in our storage. And the query, as I mentioned in the past, is not doing a whole lot. Right? It's just going to take whatever's coming in for that stream, and it's going to push it out into our data lake coming in from the input hub. And I do chuck on an extra time, so we have a review time on the record that's coming in, but we also have an event processed UTC time. That's something we pick up from Event Hub that we can tag it, when did the record actually get processed? So and you can then use that to determine if you're seeing any lags in your data. Maybe you're not scaled out enough. The data is going out to a Data Lake Store, which also has a dashboard here. We can see the volume of data we're using. I only run my data factory periodically. That's why we're not seeing a steady climb. We see jumps and bounds in here. But we can have a look here, and we can come into Data Explorer, which lets us go poke through what has been stored up here. And if we come into Stream, Raw, I called it Remarks, Year, Month, Day, and we can see that each hour on any given day has the data being created, and that's all just from what we set up in Stream Analytics. I didn't have to do any other work. It just comes in here and dumps it out. So we have it coming into Event Hub. We have Stream Analytics pushing it out to our Data Lake Store. Now we have a data factory. And the data factory is easier to look at when we look at the author and deploy, how the scripts that are used to create these. So for this data factory, we need 3 services. We need an Azure Data Lake Analytics account, which is a compute service. We need our Data Lake Store, which is where all our data is, so it has to know how to get to that. And you'll notice that, if you can, that I have a storage account here. When Data Factory runs a Hive script or a uSQL script, that script is not in the Data Factory itself. It lives out in a blob storage account. And the Data Factory will go and pull that file into whatever system needs to run that script for you. We have a bunch of data sets, which are the gates from one activity to the next, and then a pipeline. And in this pipeline, you set up one or more activities. And so you can see my type here is Data Lake's uSQL, and it has a script path and a script link service here. And that's just say, I want you to go to this container in this blob storage, grab this file, and submit this to Data Lake Analytics. But on the way, I have some parameters here, and it will inject declare statements at the top of my uSQL as variables at the top of my script so that I don't have to hard code anything in it. I can just take the variables out. And again, so when we're looking at, we only want to process the last hour, we have a slice start and slice end of every time the data factory runs, and we can use that to pass it in and tell it you're only going to run for 1 hour, right? So only go in starting at this time, take 1 hour's worth of data to process. It takes my input, and it has a scored output set too. So when we go to the next activity, it's also waiting on scored output set too. So that one can't execute until the first one does. So it is executing against the Data Lake Analytics, and Data Lake Analytics has its own dashboard. In fact, we should probably come up to the top. And this is what you'll see in here, a number of jobs. You'll see a bunch of failed ones. I started getting fancy with the query today, and it started failing, so I got a bunch of errors in there. But you can see how many times the job is run. You can see the compute hours at the bottom, and for Data Lake Analytics, you're generally getting charged for compute hours, so you can see what's going on with those. But if you want to dig down further into what's going on with the Data Lake Analytics, you can come right in here and look at the jobs. And we can take this job that we just ran, or the one I ran right before it, and it gives us very similar information. It shows you how the job broke out and how it executed. I think if we take one of these other ones, it too shouldn't have too many nodes. Oh, but this one has too many nodes. But this one, oh, this was the roll-up aggregate to our global CSV file. And so if we go back over to our data lake store, I'm processing the stream raw into stream processed. And again, so we have the remarks. These are broken out by hour, and you can see, or by day. And again, so for each time it ran, I get a results file. And then on my second sweep, I create an aggregate file. And on the third sweep, we create this constant file, global CSV, that we want to use to visualize on Power BI. So then we can come out to Power BI. And this is, I'm not a Power BI expert, so it's not the prettiest dashboard. But it's a dashboard that shows you what's going on. So we've processed about 2 million records so far. You can see a big spike because I had a problem with the system and I had to reset it. But the data was all on my Event Hub, so I was able to reset the time, and it just kind of blew in a whole bunch of data at once and some other graphs. But some of the great stuff about Power BI is I can use natural language on it and ask it questions. So I want to see total versus positive by product ID. And it gives me this graph that gives me, I can come over and hover over these things, and it says, oh, that's, I've got a product ID, here's your total, here's your positive comments. But what if we do where total is greater than 10,000? Right? It gives us a different view. And I've been running quite a few of them, and again, because it's the same files. So when it's greater than 50,000, we can dig deeper and deeper into the data with some of these natural language queries. If you have a Power BI expert on your team, they can come in and make pretty dashboards out of this data. But this data will be updated regularly, coming from that whole pipeline we have running. And if I leave this running all the time, it is actually executing. There is a web job that keeps pounding away on the stream. I turn off the data factory because I don't really need it to run all the time, but it could run all the time, and this Power BI dashboard would be updated regularly. And we can set a schedule for it. Okay, so we walked through a little bit about what data scientists talk about, how they talk about data, some of the terminology, features, labels, training data, samples, supervised, unsupervised learning, talked about what needs to be in, to solve a machine learning problem. You have to have your sharp question. You can answer it with a name or a number. Your data has to be relevant, connected, accurate. You have to have enough of it to solve your problem. We learned about prepackaged ML models, models that you can build on your own, ML versions, briefly skimmed deep learning, and then went into solving another problem where we had that website and showed you all of the components. If we tried to build all that during this session, there's no way I would have gotten through it. We'd all be here late and you'd miss the party, and I didn't want that to happen. So we've got some resources. So you can revisit any of these build sessions on Channel 9. You can go to Microsoft Virtual Academy, learn some more. All of the products that I talked about in that architecture flow are from the Cortana Intelligence Suite, and you can go check out the Intelligence Suite. There's just a massive amount of services that are out there. Again, I couldn't talk about all of them in one session. We'd just never get through it. And AML Studio to get started. Now, if you have an Azure subscription, ML Studio is free. If you don't have an Azure subscription, you can go in and get a free 30-day trial, I think, to try it out and try building some models and give it an example. We have some related sessions to these kinds of topics. So tomorrow at 9, we have Open QA, maximizing your data and leveraging AI. At 12:30, we have let knowledge APIs utilize the power of the web and improve your apps. And at 2, there's deep learning with the Microsoft Cognitive Toolkit, and that's more into that deep learning space if you're interested in learning more about that. It is really fascinating, but it is considerably more complicated than the stuff I talked about today. And then the remainder are sessions that have already happened here at Build, but will be available in the next couple of weeks. on Channel 9. So serving AI with data, how to run AI at petabyte scale, built-in machine learning with SQL 2017, with Python. Of course, it also supports R. But there's a lot of great sessions there and a lot of great knowledge to be had by looking over some of those sessions. So please complete an evaluation form. So these are really important for us at Microsoft to understand how people are receiving these talks, to see, are we giving you what you want? Is there other things that you want to hear about? Again, hugely important to us as a whole, that will just make next year's sessions and other sessions we give much more beneficial to you as the attendee. And that's it, and I finished 9 minutes early.